have a chance to talk to you today. So now can you see my screen where?
We can see the screen.
Okay. So yes, so the topic of the talk is going to be about shadow tomography with generalized measurements. This is actually a very simple project. And let's put it like this. This is our attempt to understand the concept of shadow tomography, how to understand the theory, and so on. It turns out that we found out that it could be understood in a relatively simple framework. So this is, could be the message of the talk would be try to give a simple view on the concept of shadow tomography. This is our purpose. And this is already written in this archive preprint some time ago. And so the content of the talk would roughly contain the following. So first, I would give some motivation for doing shadow tomography. What is it and why is it interesting? And I explain the protocol, which is by now quite famous. It's quite recent. It's I think 2019 or so. By now, it's already quite famous. And then I explain our attempt to understand this protocol, and I try to explain how the protocol could be understood in an easy way. And through this, I would explain why we need generalized measurements at all. And then I describe the framework that we propose. And right after that, I explain the properties that follows, which is follow rather directly. So by the way, if you have question or anything not clear, please let me know immediately. You don't have to wait until the end of the talk. So what is the problem that we are facing with? Imagine the following. So nowadays we all have quantum computers at some level. It's maybe not perfect, it's still noisy, and the number of qubits is still very low, but still we have something. And we are trying to make use of these quantum computers as much as possible, or at least get ourselves familiar with the concept of using a quantum computer for certain physical tasks. One of the tasks that could be a very interesting direction would be quantum simulation, for example. So what does it do? So basically you have an algorithm, you do it on the quantum computer, and end of the day, you get a state on the quantum register of the quantum processor. And the question is, how can we extract information from this quantum state? Probably this depend on the purpose a bit, but if we want to do it generically, the question probably is, how can we save this quantum state so that later on we can analyze it? Naturally, if we have the quantum memory, this is easy task. We just put it there, but the quantum memory is extremely expensive. It's not so easy to do. So the simple way is to ask whether we can store the quantum state or the information about the quantum state that we are interested in classically for later analysis. The question is whether this is possible. The simple way that we used to think about is certainly state tomography. What does it mean? It means that the information in the quantum state of the system is totally contained in the density operator rho. And what we do, we just have to measure and then infer the rho. For example, if you have just a qubit, yeah, it is just a qubit, and the qubit is in certain state. You can write the state in the following way. So you have the identity plus the polymetric with certain coefficient mi. And what you have to do it in order to infer the density operator is to measure this number mi. And this is given directly by the measurement of the Pauli observable in x, y, and z direction. And then you can somehow reconstruct rho, for example, by means of least square estimator, in the sense that you claim that the state rho is such that the statistic theoretically given by itself should not be deviated so much from the statistic that you measure, MI here. So this already, oops. Can you see the full slide actually? Because for me, the last line is not so, it's not shown.
The last line is the expectation of X. Is that the last line?
Yeah. So, this is okay. So, so with the density operator, you can do anything or any sort of analysis you want to do. For example, if you want to compute certain observable X, you certainly have to simply insert this density operator, which you estimated, put in there, compute X. So this, you can analyze anything you want to analyze. However, this is not scalable. Why? Because you see immediately, if you have n qubits, for example, the dimension of the system is going to be 2 to the n. So this is exponentially big. And in addition, if you look at the error in the rho, measure, for example, by chase distance, then the chase distance is also increasing in the error in measuring each of the elements. So in all, this is quite badly scaled. If we look at how the current quantum computer developed, we already have a problem. Yeah? If we have 49 or already 50, 72 or 128, this is already, well, maybe 50 is still possible or 49 is still possible, but 72 is already impossible, I believe, and 128 is already clearly impossible to do tomography on that much qubits. So we have a problem that we have to face with. And in this situation, probably the sensible question is to ask, is it really important that we have to estimate this exponentially large matrix rho? In fact, most of the case, we are not interested in rho itself. We never use the information or hardly use the information in the elements of rho, in the matrix elements of rho. We only use certain derivative information from rho. For example, we want to compute certain observable, or we want to compute the entropies or something like that. Yeah? This is not, the rho itself is not something we are interested in. So shadow tomography is a method which is in fact very much similar to normal tomography, but in a way it processes the information or processes the data in a way so that you can actually get around of the direct estimation of the elements matrix approach. So the message is that with shadow tomography, even when the error in the interval is large, the observable can actually still well estimated. And in fact, we don't need to estimate or store rho directly, which is exponentially big. We don't even have enough classical memory for that. This has been discussed extensively in computer science literature. So you can have a look at this reference and the reference then. However, it become more visible to physical community through this particular article, which put a practical protocol that one can use to carry out shadow tomography. And how does it work? The framework looks as follows. So you have a quantum system like before. Yeah? You have prepare the quantum system on certain number of qubits, like a resistor of the quantum computers. And what you do, what was proposed to do, is to do a random unitary acting on the system derived from certain ensemble of unitary operators. And then after that, we do a measurement in the computational basics. And then you store classically the outcome of this measurement. So this is clearly a classical data, which is just the arrays of 0 and 1 because of this measurement in the computational basics. And everything is pushed toward into the prediction phase, where you do data processing in a way so that you can actually directly infer the say quantum fidelity or two-part correlation or entanglement witnesses and so on directly from the data without directly writing down the density operator. So this is a rough overview of this. Let's look into it in a bit more detail. Yeah? How is it data is collected? This okay, here we say we prepare the system and do a random unitary evolution on it. But equivalently, we can think of we actually prepare the system is the same in the first step. Equivalently, we can think that we make a measurement in a certain basics of a unitary operator U. Yeah? This is equivalent because you rotate on the state is the same as rotate the measurement in the reverse direction, so to say. So this is equivalent formulation. And then what you do is just have to record the obtained outcome of in the basics associated with a unitary operator. Yeah, so you repeat this process several times. So you go m times, and then each of the time you record this on a string of outcomes BU. End of the day, you have a string of outcomes BJU for j equal to 1 to m. And how does it work? How do we process? For example, how do we estimate observable x? For example, yeah? To do so, now I describe the technical calculation what one had to carry out. I try to explain it a bit later, and this is actually the main part of our talk is to understand how to understand this formula. Yeah? So first, it define from the it define a channel which acts on the state of the system, which is simply given by this formula. How does it treat? So you think that you make a measurement on the B, and then on the row, and then you collapse the system into the basics BU, and at the same time you can think of the system is prepared in the state BU. So overall you have probability here and the state after the measurement, so to say. So have a channel like that, and for each of the outcome BU you have from the data, you can associate a state by just simply inverse this channel, assuming that it's invertible. Then you just simply have to inverse this one, I think, on this particular operator and get back a row head. You can think of this as row head as something like already some estimation of row. So this is some replacement at the level of a single data point. So this is one of the estimation for you. And how do you estimate an observable x? Well, this is simple. You just have to estimate the observable x for each of the shadow. Yeah. So because now you have a series of outcome BJU, and then you just have to compute the mean values for x for each of the outcome, and then you have to average over all of them. And this is just all you have to do. And then there's certain more technical thing like refinement with median of means, asymptotic optimality, and so on, which I'm not going to discuss now. I'm trying to explain how to understand this formula in the first place. So before going to the formula, I just mentioned briefly why this is scalable, why this method is scalable. The most simple way to see is to consider the case where we have n qubits here. Yeah? The simple setting would be you choose a random unitary on the first qubit, random unitary on the second qubit, and so on. You choose a random unitary on the nth qubit in the certain example. And according to the formulation, the shadow estimator is actually simply the tensor product of different estimate of different estimator on each of the qubits. So you have a string of tensor product like that. Yeah? And now, if the observables that you are interested in is of this form. So you have also tensor product over different qubits. You can actually do it that quite directly, because now you take the choice of rho BU and X, then it simply factor out of this one and this one, factor out over each of the qubits. Yeah? So end of the day, the average X you have to estimate is actually average over the whole data set. For each of the point in the data set, you can efficiently compute is simply the product between different values estimated for each of the qubits. So in this way, you never have to store the whole big matrix rho BU, but you can actually directly compute this average for each of the qubits and just simply have to multiply them with each other. So rho is never written down explicitly, and that's why it's scalable. It's fast, and you don't have to store big matrix at all. Okay, now come back to the. Oh, yeah, you want to ask?
May I ask a question? For the case that X are not are not product state, they are linear combination. Would they be what's the form? Is just the same way with linear combination, or I think it's more complicated, right?
Yeah, of course. In principle, if the X is really complicated in the sense that it's really global operator, yeah, it could be complicated. But in most of the case, for example, correlation is of this form. Or in the worst case, you can have the X spanned by certain factor or product or operator like this. So it's most often in the application.
Okay, thank you.
Yeah, so if that is clear, now let's come back to the question we asked before. How do we really understand this channel? Yeah, this is the channel that we put before, and how do we really understand this shadow formula? Actually, the question is, why should this whole framework work in the first place anyway? So one of the very tempting interpretation is the following. So think of this measurement as something that measure on the state and prepare the system in the state corresponding to the collapse outcome. So in a way, it suggests that this post-measurement state, so after the measurement, BU, Kepra, is somehow important, and something like the reverse channel onto the post-measurement state to reconstruct rho in a way. What I'm going to argue now is actually this tempting interpretation is maybe not so natural. There's maybe another more natural way to look at it. But first, let's see why this is work at all. So first, we just have to look into the formula whether it converges. So the first question we can ask is whether this actually converges, in the sense that if you have infinite number of data, so you send m to infinity, whether this average of rho actually converges to rho. So in that sense, you actually estimate all of the observable, because this average of rho is correct. Yeah. And why this is actually choose? This is because I CU on here, on this expression here, you get this one, equivalently, you have to prove this converges to that. Assuming that CU is invertible, yeah, this is equivalent. And why is it true? This is simply because you plug the definition of this rho hat into here, and this CU absorbs this CU minus 1. So you have directly sum over this post-measurement state. And now in the limit of m to infinity, you just have to replace the average over the data set with the average over the probability. And so this is average over the infinite sampling, and this is simply replaced by the average over the probability weight of each of the outcome. And in this case, you can actually have this directly formula for the CU here, exactly what you expected. And therefore, this actually converge rightly. However, back to the interpretation that here we are really need the post-measurement state of the system. However, if we are somewhat familiar with quantum information theory, we know that post-measurement states are not only are only determined for ideal measurements. ideal measurements are rather special case in quantum physics. The most general model of measurement would be called generalized measurement, or more technically, people call it POVM, positive operator value measure. And a generalized measurement of n outcomes would be described by n operator ek. Each of them positive and sum up to identity. And the statistic of the outcomes is given by choice of rho ek. However, for POVM or generalized measurement, there is no unique post-measurement state for each of the outcome in principle. Sometimes it happens that there's a natural way to associate a post-measurement state, but in the most general case, for example, if you take this ek to be identity, for example, this is not clear what the post-measurement state of the system is. Therefore, the natural expectation, according to our perspective, would be information from a measurement is actually independent from the post-measurement state. So one should not base only on the post-measurement states. So the interpretation that we tried to think of before seem not to be so consistent with this philosophy. We emphasize that there's already some other approach which trying to do shallow tomography by means of trying to synthesize this post-measurement state of the measurement. But this is, as I said, this is not what we are going to do. So now, if we get rid of this interpretation of the post-measurement state, how do we understand this channel? And how do we understand this conversion? It turns out that this conversion is actually independent of whatever you actually put in here. For example, if you put this state to be some other state, tau BU, and you make sure that tau BU is chosen such as this is invertible, and then you can still have this shadow or replacement of the shadow given here by now this C tilde, C minus 1, acting on the tau BU. And you run exactly the same proof before. You want to prove this converges to rho. This actually also converges. Yeah? So this exactly the same proof works like before. There's nothing changed, in fact. So now even the conversion of the CU doesn't uniquely define this operator CU, this channel CU. Therefore, this channel, the interpretation of the channel CU is still a bit of mystery. It's not guaranteed by the conversion. So here come to our framework that we propose how to understand this. So this was a mystery that for me was very difficult to understand at the beginning, and this is what we propose to interpret. And it's natural not to do with shallow tomography with ideal measurements, but actually for generalized measurement is even a bit simpler. The design theory should work for generalized measurement, because in this framework there's no reference to the post-measurement state at all, and this is naturally what we expect. Yeah? And lastly, it should not based on the conversion, only on the conversion of the estimator. Okay, conversion is good, it's clear, it's good, but it's not only the support of the shadow to be a good estimator. And why is it a good estimator at all? We have to answer differently. So before going into the detail, I repeat what generalized measurement is and how do we understand them, or how do we imagine about them. So as I already said, the generalized measurement is described by n operators, which are positive and sum up to identity, and the statistics are given by choice of rho ek. This is each of the ek are called the effects. Ideal measurement is one of the example where you have the effect as the projection on the spin up and spin down in this direction, for example. This is one of the example. But generalized measurement can, in a way, have more outcomes than two. So you can think of ek pointing in several different directions on the Bloch sphere. And how do you implement it in experiment? Usually this is implemented by couple the system to appropriate antenna and then make a measurement on the antenna, because the antenna can have several levels, and then you even make ideal measurement there, you have several different outcomes which corresponding to the reduced on the system, this corresponds to generalized measurement made on the system. Other example, for example, if you have randomization of sigma x, sigma y, sigma z, this is actually considered to be a POVM which have a sig effect pointing in sig direction like this. Yeah? Yeah. And this is actually something quite well known in measurement theory. This is called pre-processing of the measurement. So you simulate POVM by means of randomization of idea measurement. The other, maybe even more interesting, is the case of noisy measurements, where the measurement have noise. For example, you cannot make a measurement perfectly project on the Z direction up and Z direction down, but actually it's only a little bit depolarized like this. You have to describe this by a POVM, which is described by effects which are slightly depolarized like that, for example. This is one of the models of the noise. Later on, we can discuss a bit more about noise and so on. And what is the framework to do shadow tomography with generalized measurements? It's very similar to before, or more or less exactly as before. Just keep in mind that generalized measurement already contains this randomization as a special case. So we don't have to do randomized measurement, but actually we don't have to do several measurements. We just have to do one single POVM, and then that's done for the data. So what we do? So first, you have a quantum processor. You have to prepare the quantum state of the system on the resistor. This is anytime you have to do this, and then we have to make a measurement, generalized measurement, a single one on the system, and you record the outcome corresponding to them. So this is the effect of them, and then you record the outcome k. So you repeat this m time and repeat. You record all of this outcome kj for each of the time you repeat it, and then you store the data. This is very similar to before, apart from the fact that you don't do randomization here, which is considered to be a way of simulating generalized measurement in any case. So how do we do data processing? At first, this slide will be a bit slightly complicated. I will come back to it again to explain. Now I just explain what step you have to do. So for a measurement with effect given by EK, you associate a map, which essentially the mapping a density operator to the statistic. So this is a map from the density operator to the R to the N, which is a statistic. Yeah? This is exactly given by this formula. Now, for each of the outcome, L, we don't use any post-measurement state. We associate each of the outcome with a probability distribution in R to the N. So this is a probability distribution, delta probability distribution, which is equal to 1 if k equal to L, and 0 if k is not L. So this is a vector in R to the N. So this is one of the basic factors. So if you want. Another classical shadow, we use the following formula, which for now it looks quite complicated. Yeah? So you have phi e dagger phi e minus 1 phi e dagger delta L. So it looks a bit complicated. However, you already have a feeling of what is going on if you think of phi e in the case where phi e is invertible. In this case, actually this phi dagger absorbs this phi dagger. So I just simply have phi e minus 1 acting on this row L. So it's exactly this inverse of this one, yeah? Inverse of this phi e. And this phi e acting on the one of the probability distribution, which is living in Rn, and give back the density operator row, or estimated density operator row for a single data point. Yeah? For an observable, you simply have to do as before. You just have to average for each of the shadow. So everything works exactly like before from now. However, how do we understand this formula? Why this formula is good? In fact, first we look at the conversion of the formula. Yeah? How the conversion can be seen. The conversion means that you average over the shadow over all of the data point. Yeah? This is the shadow that we use. And this is equivalent to average, because we do the same trick as before. Yeah, we average over the data set is the same as average over all of the probability. Yes, sorry, this is probably a typo. This has to be J. Yeah? So this simply plug the definition here, and then you have to average over, replace the average over the, and then you pass this average over L of this over J of this delta L in here. What you get is actually the exact statistic of the measurement. And therefore, what you do is actually acting on this operator on the statistic. So if you in the infinite sampling limit, this is the exact statistic of the measurement. And you just have to act on this act operator on this statistic. It turns out that why this formula is actually this formula is the least square estimator or least square solution to the problem of estimating rho of estimating rho, so that the statistic is exactly described by this statistic that you measure in the infinite sampling limit. And it's quite straightforward to derive this formula. So I don't derive it here, but I just claim that it's just a least square solution. There's nothing so special about it. So in conclusion, we just claim or generally claim that general classical shadows are actually simply least square solution of the density operator for single outcomes. So this work at the level of single outcomes. Yeah? The statistic, when you have average over all the outcome, give the exact state. For each of the single outcome, you give still the least square estimator of that particular outcome for that particular outcome. And so now let's try to connect to what we had before. For example, the definition of the measurement channel CE. How do we define CE? So CE here is defined by means of, if you look at this formula, yeah, if you look at how phi E is defined as before, and phi dagger, just a few line of calculation, you get phi dagger like this. And then you see that CE, you can define it like phi E dagger, phi E, then you get exactly this formula here. Yeah? And if you write explicitly the formula for CE, it looks like this. So sum over K, choice over rho EK, EK. Very similar to before, except from the fact that this before you have the BU. Yeah? It's very similar. However, here we are not going to interpret EK at all as the post-measurement state of the system. There's no such interpretation. It's in a way a bit of coincidence such that phi dagger phi E give you that formula. And how does it connect to the case of ideal randomized ideal measurements as before? In this case, as we already said, randomized measurement can be considered as one of the generalized measurement given by 1 over, so the effect corresponding to the BU given by 1 over U, BU, BU. Yeah? If you plug into the formula of CE, you get this formula of the channel. In fact, this is not exactly the formula that you had before for in the framework of randomized measurement, but you have a factor of 1 over U here sitting. However, if you act rho, you compute this is shadow rho BU. This actually you have to take the inverse and acting on the EK. In this case, you have to act on the effect, yeah? And the effect have one more factor U, and this cancel exactly this E2, and therefore you get the exact the same formula as before. Yeah? Therefore, it's coincide with the formula before for the shadow. Okay, now I was trying to motivate that this is something natural way of thinking about this HKP shadow tomography that I described before. So it have at least a very explicit explanation of why this converge and why this work like that. Yeah? It's independence of post-measurement status. This is what we already expected from the beginning. The general framework should be like that. Yeah? And it generalized property of HKP shadow tomography in a very natural way. So there's nothing so different in terms of properties. But there's also further property which is quite interesting and associated to this scheme. For example, for POVM, then it means that if you do, in certain cases, you can do POVM and you don't have to do randomization. In experiment, randomization of unitary can be a bit difficult because you have to recalibrate the device all the time. Each of the time you do random unitary. Yeah? And And then we can also understand the formula for classical shadow under symmetry in a much more general ways. Or we can analyze noise very consistently. There's nothing difficult in analyzing noise because general measurement already includes own description of noise. And lastly, it can be optimized. This is quite interesting point, in fact. So now I want to ask how much time I have still. Okay. I cannot hear you.
I think you roughly have 20 minutes.
Okay, this is quite enough. But by the way, do we have a question or so far? Yeah, because I cannot see you on the screen. So actually, if you have question, you have to say something so that I actually aware of it. Okay, if there's no question so far, I go on a bit more. Okay, first, the first point. Now I'm going to ask to describe one of the property that I'm listing here. In particular, the last three property. First, the symmetry of classical shadows, how to understand it, and then I describe a bit of how noise can be analyzed, and lastly, I describe how optimization can be carried out. So first, symmetry of classical shadow. So for some time ago, people realized that sometimes the formula for classical shadow is extremely simple. You can easily compute it with a one-line formula. So before you have to invert the channel and so on. Okay, it's not so a big deal with a qubit, but if you have a bigger system, it could be a bit problematic. Yeah? But in any case, in many cases, this is done very easily. For example, for the qubit, okay, in this case, again, it's quite simple. You make measurement in x, y, and z direction like that. The shadow would be simply given by this particular simple formula. So it's quite easy. And the question is, how do we understand this? Why this is so? In many cases, associated with property of the unitary design. And later also got extended a bit more further. Here we pointed out that it is very directly characterized by the symmetry of the measurement, which is not necessarily the property of a unitary design, or at least not very directly. In many cases, directly related, but it doesn't need to be exactly the property of a design. Why is it so? In fact, it's extremely simple. So think about this example. I just described this example. You have a qubit and you can make general measurement which form the octahedron or tetrahedron or the cup or the cup octahedron and so on and so forth. Yeah? Take the octahedron, for example. This is highly symmetric measurement in the sense that all of these points are in fact equivalent. This is called uniform. So all of the effects are equivalent. They can be related by a rotation, by a proper rotation. And it's even more interesting. If you pick up one of the point here, and you see all the rotation that move the object into itself, but leave this vertex invariant. So this vertex have to be fixed there. So what are those? You have 90-degree rotation over the z axis. And importantly, you can realize that because this rotation fixes vertices, it means that the effect that you are associating here has to be commute with all of this rotation. But something that commute with all of this rotation can only be either the identity or the projection on this direction, spin of the direction in this axis itself. And this is the only possibility of choice. So in general, the effect can only be the linear combination of this identity or the projection here. And this argument actually works exactly the same for the shadow. It's two lines of a proof to show that if the measurement have the symmetry like this, the shadow for each of the outcome you associated here would have exactly the same symmetry. And therefore, the shadow is also a linear combination of the effect itself, in this case, the projection, plus the identity. This is identity. And then certainly with this formula, explicit formula, you can directly put A and B explicitly. Not so important how what I wrote here is just explicit formula for it. It's not so important. The message is only that if you have certain symmetry, which first it has to be uniform, and second it has to be co-rigidly symmetric in the sense that the stabilizer or the rotation that is fixing this point fix exactly also the projection here, because this is the only projection that comes with this on this rotation. This is co-rigidly symmetric. The concept was actually developed some time ago in a very different context in this paper here. And then now we use also exactly the same thing to show that this is probably the most general way that simple formula for shadow tomography can arise. Okay, now I move to the next property that I promised, namely analysis of noise. So first, before going to the analysis of noise, we need something to quantify the quality of the shadow tomography or shadow estimator. Suppose we want to estimate a certain observable X. Yeah. So in order to see the quality of this estimation, the important quantity would be the variance of the estimator. Yeah? Is it control how fast it converges? If the variance is big, this means that it converts slow. And if the variance is small, it converts fast. In particular, if the variance is 0, it means exactly the same converge directly in the first measurement. So how do we put the variance of an estimator? Yeah? This is how you compute it. So for each of the, so what we do first, for each of the effect k, the probability happen for the ek is like that. And then the square of the estimator corresponding exactly to the choice of rho k x square. So this is the estimator that you have, and the variance, of course, you have to minus the mean of the x. It's given by this formula. And now we want to estimate this or upper bound this by something that is independent from rho. So we want to have something that is independent from the state that you put in, just depend on the measurement that you make and depends on the observable that you want to do. So this is in the sense you do worst case scenario. You want to somehow maximize over rho. Actually, the first step is to remove this thing. Of course, if you remove a square thing, square terms, this is still increased. So this is proper upper bounded by this one. And then you maximize over rho. Now it's easy because it's a single linear in rho. So this is simply the maximum eigenvalues of this operator, which is clearly positive. So we end up with the definition of shadow norm, which is the same as the definition by the nature physics paper that I cited before. This is maximum eigenvalues of this sum. And now the quality of a set of observable. So suppose you have m observable, then the quality roughly for now, we can assume that xj somehow have the same unit. Then this would mean that you simply have to look at the maximal variance of the whole set of observable. So it could be the worst case scenario. And yeah, this could be the at least for now the figure of merit to consider the quality of shadow tomography of a set of observable and for certain measurement. And how does it change with the addition of noise? For example, the case of depolarizing noise in the sense that you have effect, and then the effect would be depolarized a bit with probability p. The device actually doesn't really couple to the system. It just gives a random outcomes. And only with probability 1 minus p, the device work properly, coupled to the system properly, and gives the right intended measurement. So this is how it looks. The kappa e square. This is how it changes over the probability of errors. This is p. Yeah? So you see that for for small p, this is changed very slowly. In fact, it diverges at p equal to 1. But of course, in this case, you have p equal to 1. It means that you don't implement any measurement. So of course you don't have any information, you cannot infer anything. On the other hand, if P is reasonably small, for example, even until 10% or 20% or so, this still the shadow norm still doesn't change so much. So it's in a way it's very robust, in fact. The other type of noise that we can analyze is the readout errors, and in this case, let's restrict to the octahedron. Yeah? The octahedron measurement by the octahedron polytope. Yeah? If you have readout errors, it means in a simple setting, it means that if you measure 0, the outcome you read could be 1. And if you measure 1, the outcome you read actually could be 0. This is only because of, for whatever reason of the device, could be a wrong signal in the device or so on. It flips the outcome of the measurement that you actually have. And in this case, the effect of the tetrahedron measurement before was given by t plus, t minus, t minus. Now it's on, if you have a probability of being wrongly rated outcome at plus SQ plus, then this is simply reduced by a factor of 1 minus Q plus. And for the case of Q minus, you read it wrongly, it means that you read as S plus. Therefore, you have this effect given by that. And similarly for the other effect here. And now for the parameterization, we call the Q plus and Q minus here. We parameterize it by two parameters. First, the average error rate, Q bar, and the asymmetric parameter epsilon. And this is how it depends, yeah? How it depends on epsilon and Q. For example, for reasonably small Q, this is 4% and 12% up to here. And this is how it changes into the asymmetric epsilon. Again, here we just want to demonstrate that this can be explicitly analyzed. And it shows that it turns out to be quite robust. This shadow tomography of observable are quite robust. It doesn't get so much effect from noise. And so this is a good news, in fact. Okay, now in the last point I want to say is that once we have this generalized framework, it's also quite easy to do optimization over the measurement. So the question is the following: you have a set of observable, which is fixed at the beginning for some reason, and I want to estimate or want to find the optimal measurement that you should perform on the system, so that the shadow norm of the set of observable, or the maximal shadow norm of the set of observable, is minimized. So we look for the measurement that minimizes things. For the random unitaries, it's very hard because it depends on the ensemble of unitaries you choose. So there's already infinite number of them. And then it also depends on how you, which probability way you choose. You could choose uniform one, but this is not the only choice. Yeah? If you use this generalized measurement, it turns out to be a very straightforward, or at least well-formulated optimization problem. It's quite simple, in fact. First, you see that the domain of the optimization is E, which is generalized measurement, and they are actually a convex domain. It's just a convex set. It could be a high dimension, but it's still convex and it's very well behaved in a way. However, the objective function is non-convex, is highly nonlinear, and so on. Therefore, the minimization could be still difficult. So what we use for now is to use simulated annealing. So you minimize this objective with simulated annealing, and this it turned out to be very robust. This is something I use quite often, and in this case, it's extremely robust. So here I show some example. Yeah, the first example, A here. Yeah, just concentrate on this figure. What we do here. So the set of observable we choose is a tetrahedron. This is a tetrahedron. You don't see the fourth vertices, but it's have 4 vertices. So there are projection on this 4 point on the orange tetrahedron. And then we use the optimization technique to find the optimal measurement. And here is what it finds. It finds that the optimal one is actually also the tetrahedron measurement, not exactly the orange one, but actually inverted at the orange one, like that. Yeah, so it's inverted. This is violet here, so it's inverted through the center. This is quite interesting structure. And the other case we try is to consider this observable as 4 projection in 4 different directions here. This is against by the orange tetrahedron, yeah? Or octahedron, sorry. And we try to find the optimal measurement one can do. If you fix the outcome to be 4, in this case, you actually find this tetrahedron measurement corresponding to this direction. Yeah? This is also an optimal measurement. This is also interesting. It's highly robust. Of course, if you increase the number of outcomes, you fix it to be 6, then you find the octahedron. In this case, you find the octahedron measurement again. So this is the same as the octahedron. Yeah? Later on, we are going to show that this octahedron measurement are somehow special. In a way, this is very robust and it's highly optimal, at least for the qubit case. Yeah? Another example we consider here is this figure is to consider random projection on the block sphere. So you take the random projection on the block sphere, you take, so it's a number of observable here. This is 2 to the 2, to the 3, to the 6 number of them. Random projection, yeah. And you try to estimate this projection. And you want to optimize the measurement so that this shadow norm is minimized. You see that first, if you fix the measurement to be the tetrahedron, which is actually CPOVM, I didn't mention that, sorry, or the octahedron, which is simply the 3 poly observables. Then you get this first tetrahedron here, octahedron there. And if you do optimization, you fix the number of outcomes to be 4. Then this line go like that. It goes a bit concentrating or converging to the tetrahedron. On the other hand, if you fix the number of outcomes to be 6 or 8, you have to get this curve. So at the beginning, if the number of observable is small, you get better solution here. It's maybe not so much, but it's still better. Yeah? It's clearly better than the octahedron measurement. However, if the number of observable is more, you increase up to the 5, for example, here, then it converges very fastly to the octahedron measurement. So it's converged to the line here. This is part of the fact that the octahedron measurement is somehow optimal in the case that you have to estimate many of the projection on the box sphere. And this turns out that we can actually prove this rather analytically. And I skipped the proof, but if you are interested, I can discuss in maybe in more private context. And the next example. So first, we are talking about shadow tomography, which is important for many body systems. So we are interested in rather more many body systems. Before the case study of single qubit, which can be interesting, but it's still only an academic example. But this optimization can also be carried out for many body systems. In this case, you consider the system of n qubits. Of course, in this case, if you do most general line measurement, this is too many parameters in any case because the dimension explode exponentially. However, most of the time you are really only interested in the case that the measurement can be factorized out, because this is also something easy to implement. This, if you do joint measurement on certain number of qubits, it's not so easy also. So you can assume that the measurement is factorizing out like this. And even more, if the qubits are somehow equivalent, yes, there's no reason that you prefer this qubit from other qubit, and that's why they are roughly equivalent to each other. You're probably very tempted to do the same measurement, exactly the same measurement on each of the qubits. So it's just a tensor power of one of the single qubit measurement. In this case, you have finite number of parameters to optimize over. The whole operator E is still big, but you still never have to write it down explicitly. It's the same as the data processing step that I mentioned before. In this way, you can also compute the shadow norm efficiently, and you can optimize over it. And the outcome is similar as before. In this case, the observable are tensoring of n random projection. So I choose n observable, and each of them are tensor ring of random projection on each of the qubits. And then just a case study. And I try to see how the tetrahedron measurement works here, how the octahedron measurement works there, and how the optimization technique works here. It's work here and work there, like that. So it's very similar to before. So, but here is the number of qubits. Also, the number of observable also increased, but it's important here is the number of qubits we are talking about. So it also converts quite quickly to the octahedron, which also points to the fact that for the qubit platform, probably the octahedron measurement is somehow quite robust thing to use for shadow tomography, which is a good news in any case. Yeah. So with that, I close my talk now. And yeah, okay, so the conclusion is that, again, this project is our attempt to understand shadow tomography in a particular way. And we propose that this could be a very simple way to look at it. It's extremely simple. It's even more general. It's, at least for me, I find rather very intuitive and simpler. So the AKP shadow tomography can be more easily understood, or the symmetry analysis can be generalized, or noise can be consistently analyzed, or the setup can be optimized. So this is all of the points that I mentioned. And by the way, there's also other paper mentioned a bit of shadow tomography with general measurement, which is given by this archive number here. However, the most general framework was not really discussed there. So this is, in some aspect, it was already they are considered, but it's not in the totally general manner that we would like it to be. So yeah, so I just want to show you my collaborator. So my acknowledgement to my collaborator. Here's Otfried Winner. This is myself, and this Jan. Unfortunately, Jonathan is not here. However, it is only in the figure. Yeah. This is a figure of our group here in Siegen. Yeah, and thank you for your attention. If you have more questions, we can start discussing the detail now.
Hello. Thank you for your talk. I may have some questions.
Yeah, please.
May I ask, what was the scaling of the data size needed for this shadow tomography? Is there any consideration here, or is there any expectation?
The scale of what? Can you repeat?
The data size M. Data size M. You average over all the data, right?
Yes, I average over all the data. Yes. So the scale of M. The analysis is very similar to this original paper by Huang and Preskin. This is the same analysis applied. I mean, we work a bit more into the detail currently, but basically it should be quite similar. Analysis is applied because you see, if you simply replace this general measurement by randomization, which is equivalent, so it's the same work that should work exactly here.
Are people interested in the size with respect to the qubit number K? I mean,
yes.
Okay.
The respect to the qubit number K. Maybe I say it again to see where is it. There's the window. No, this one. So you see it already here, right? I mean, in this case, have n qubits, and the qubit number K is n here because I choose n random projection. Yeah? And the natural thing is this shadow norm actually exponentially explode in number of qubits. So it's if you do this tensoring over the number of n qubits. However, most of the observable are not of this form, are not of the most extreme form like this. Usually, for example, two-part correlation, you just have 2 qubit observable. Yeah? You don't have to tensoring all of them. This is only for the case study. So you see this is a log scale, and this log have to be divided by n, and you see that it remains stable. Particularly for the octahedron, you can directly see that it's exponentially big.
Okay, sorry,
Yeah.
can you explain this figure more? Because I do not fully get the point. You mean for large qubits, it all converge, most of them converge, for which case I cannot tell for the tetrahedron or octahedron.
Octahedron, yes. So for the case of n equal to 6 and 8, it converges to the octahedron. This, in a way, you can easily understand it already from the previous picture here, right? This is for this manipulated system. This is for single qubit. Probably this easier to see. You see that if you have so many observable, end of the day, you essentially want to estimate all observable, or in this case, all of the projection on the pure state of the qubit. This is the case. And you see that if you want to do this, one can prove analytically that the octahedron is actually the optimal. This gives the optimal shadow norm if you want to estimate all projection on the pure states. Yeah. And you see that you see this converging is because when you increase the number of observable, this is converging exactly to this proof. And why is it the same here? This is here because first we see that the qubit are equivalent, and each of the qubit you derive a random projection on the qubit. Yeah? And then if the qubit are only equivalent, in a way you can think of all of this random projection on the all of the qubit equivalently have the same effect as the many random projection on a single qubit. So in a way it collapses to this very similar problem, and therefore you can expect that if you increase the number of qubits, the average effect on one of the qubit in the optimization, yeah, this also converges to the scenario where you have infinite number of projection on the same on the single qubit. Does it make some sense?
Yeah. Okay. Yeah, it makes sense. Thank you.
Mm-hmm.
Sorry, I may ask a basic question.
Yeah, sure.
For generalized measurement, do we still interpret all the trace over as the probability? Because they are not actually projection, because they are not orthogonal. So do we interpret them as the probability? Do you understand my question?
Could you maybe point to one of the slides so that we maybe I understand it better?
Can you just go back to the introduction of the generalized measurement?
Here?
Yeah, probably here. For the generalized measurement, the condition is the summation over all EK equal to identity, right? Mm-hmm. But the EK may not be projection themselves. Mm-hmm. But the quantum mechanics, usually we interpret them as the probability because they are projections. So, yeah, I'm just asking, do we interpret them as the probability, or we can just do them from counting the number collected from the measurement, so that, yeah, have this number?
I think the impression that quantum mechanics interpret probability from projection is quite special. It's a very special case. In fact, this is what I would try to argue here is actually probability is more related to positive operator. So if you see this formula, for example, yeah, it's almost not probability. This is EK, apart from the fact that they are operator. This is also positive, and they are sum up to 1. If you think of identity as 1, it's already mimic the probability. So the probability replacement in quantum mechanics is more proper to do, not with projection, but actually with positive operator in general.
Okay, I see. So for the case of the simplest one, the XYZ direction, this right figure, yeah, and yeah, the left figure figure here. Why it is called randomization? Because it's just a sixth direction.
Yes. So I'm saying if you do randomization in the sense that you coin a probability of 1/3 and you flip a coin, yeah, and you choose probability to measure sigma x with probability 1/3, or choose a probability to measure sigma z with probability 1/3, and choose to measure sigma y with probability 1/3. This is exactly equivalent to one single generalized measurement with sig effect. So this is two different ways of implementing things, which are end of the day completely equivalent. Description.
Okay, so the naive way is just do the flip coin for the probability with equal 1/3 probability for all three directions, and then to the two outcome measurement for each direction.
And then this gives a pure simulation of the generalized measurement. However, this is a very special case. In general, for generalized measurement, some generalized measurement you cannot do like this. So, for example, the CPOVM you cannot do like this. Does it make sense? Well, the CPOVM I also plotted it here. Yeah, for example, this you can do like that. You can do randomization in this direction, that direction, and that direction. But this tetrahedron you cannot do like this.
Yeah, yes, and then for the case of the unitary rotation from paper of Ximing Huang, how is that possible? Because the rotation is for all direction, right?
No, the rotation random unitary depend on the ensemble that you use. You could use the so here. So this for certain ensemble U calligraphic here, you fix it. For example, you can fix it to be the Clifford ensemble. And then this would give you this three randomization in three direction. Yeah. So this U, you have to fix the choice of U at the beginning.
Okay, it's just like the three direction case. Yeah, just
Yes.
Yeah, fix that. Okay, thank you. Okay, very good. Thank you. It's very interesting. Thank you.
No, thank you. Thank you for the question.
So is there any questions from the audience? Okay, if there's no further question, let's thanks today's speaker, Dr. Nguyen.
Thank you.
Thank you.
Yes. Hi, Dr. Wei.
Yes.
Yeah, I'm Lien Nguyen. I'm also doing this kind of problem related to tomography. So maybe sometime can I discuss with you for more questions?
Yeah, sure. Just send me an email and then we arrange some Skype or something. Sure. I'm very happy to discuss. Sure.
Yeah. Okay. Thank you very much. And yeah, so may I have a quick question?
Yeah, sure.
In this case, do people consider the rank for the density matrix to be measured? Because in the low rank case in the tomography, people usually have some trick to do the efficient way to do the measurement for in tomography case.
Yes, this is actually a good question. In fact, I have not seen it, but this literature is developing also very fast. So I'm not so sure that there's nothing done yet. But I have not seen it. But I think it's a good thing to think about.
Okay. Yeah, that would be good. Yeah, maybe we can discuss more.
Yeah.
I'm Lien. So may I ask which country do you come from?
I come from Vietnam.
Vietnam. Okay. So you don't speak Mandarin, right? Okay.
Yeah, I don't. Sorry.
Okay. No problem. Yeah. Thank you. Yeah, it's very interesting work.
No, thanks.
Okay. Nice. Thank you. Yeah. See you sometime.
Yeah, see you.
Okay.